Okay, so in this video I'm going to talk about the Lambert W function, or the omega function, or the product log function. Now what I've done here is I've drawn x e to the power of x, which I'm calling f of x, and I've also drawn the line y is equal to x here on GeoGebra. So what we need to do with x e to the power of x is reflect it in the line y is equal to x. So if we do that, we'll get this kind of a function here. It comes up along here like this, out in here, and out this way. It's roughly the image of x e to the power of x in the line y is equal to x. So this function that I've just drawn, or this graph I should say that I've just drawn, would be the image of this graph here in the line y is equal to x. Now the reason I'm doing that is I'm taking the function f of x equal to x e to the power of x, and I want to find the inverse of this function here. So this theoretically would be the inverse. However, if you look at this graph that I've just drawn, you can see that it's actually not a function, because if you take a vertical line down along here, for example, you can see that this particular input here has two outputs, here and here. So this function is, this graph I should say, is not actually a function. So we've got to go back to square one again, and what we'll do is just have a look at our original function, this one here, x e to the power of x. Now we can see actually that that function is actually not injective by the horizontal line test. So if you were to draw, for example, a line across here like this, horizontal line, you can see that it cuts the graph in two places. So therefore our function x e to the power of x, f of x in other words, is not injective, therefore it's not bijective, therefore it doesn't have an inverse across this particular domain. So what we've got to do is just take part of this graph. I'm just going to take from somewhere around here onwards to the right. In other words, we're just going to take somewhere around here and look at all the x values to the right of that out into infinity. But what value down here am I going to take? Well, let's do a little bit of differentiation and work out what our minimum value down here is. So if we take our function, our original function is f of x, and it's x e to the power of x. We want to differentiate that first of all. So if we differentiate our function by the product rule, it's u dv dx plus v du dx. So we just end up with x e to the power of x plus e to the power of x. Or we can just factorize out the e to the power of x to give us x plus 1. Now in order to find our minimum, what we need to do is let that equal to 0. So we've got e to the power of x, x plus 1, let that equal to 0. That'll give me, let's see, e to the power of x is equal to 0, or x plus 1 is equal to 0. E to the power, e is just a number. Raise that to anything and you're not going to get 0, so this is not going to work here. So we've got to look at x plus 1 is equal to 0, so that will give me x is equal to minus 1. So at x is equal to minus 1 here we've got a minimum. Well, let's just prove that as well. So what we would need to do is just differentiate again. So we want to do f double prime of x. Remember, this is our f prime of x, our first differentiation, if you like, of f of x. So again, by the product rule, we can do u, which is e to the power of x, dv dx, which is 1, plus v, which is x plus 1, times du dx, which is e to the power of x. So let's just simplify that. We got e to the power of x, which we can take out, and we get 1 plus x plus 1, which is just e to the power of x, x plus 2. So if we put our x value in there, so x is equal to, we're saying here that x is equal to minus 1. So if we put that in, we get e to the power of minus 1 times minus 1 plus 2. That'll give us, let's see, 1 over e to the power plus 1 times 1, or just 1 over e. This is positive, greater than 0, so that implies we're looking at a minimum. Okay, so we have a point here at minus 1, we have a point here at minus 1, anyway, minus 1, and let's just find the y value that that would give then. So we have x is equal to minus 1. I'm going to just put that into our original function. Remember, our original function was f of x is equal to x e to the power of x. So we have, let's see, f of minus 1 is going to be minus 1 times e to the power of minus 1. That is minus 1 over e. So our point here is minus 1 and then minus 1 over e. So our minimum then, is minus 1 minus 1 over e. Okay, so let's have a look at drawing an inverse function then. So if we take this point here, which is minus 1 over e, just reverse those points. We're looking at starting, let's say, somewhere around here, coming up along here, and then out along this way. So that would be the inverse function of our f of x, taking the original domain from here out. So this is going to be called our Lambert W function, with a domain of this here with the x and y reversed. So we're going to start at minus 1 over e minus 1, and we're going to go out to infinity then. So that's this point here. Let's summarize what we've done to date. We have our original function, which was f of x equals x e to the power of x. Now that had a domain of minus infinity to plus infinity and a range of minus 1 over e to infinity. So we found we couldn't use this domain here because the function wasn't injective, so it didn't have an inverse, so we had to restrict the domain. So what we found was that we restricted the domain, the new domain, to, let's call it a new domain, to minus 1 to infinity, and we found the new range is minus 1 over e again to infinity. So our inverse function then f inverse of x, which we're calling omega, or Lambert W function of x, has a domain, goes from minus 1 over e infinity, and the range is now minus 1 infinity. Okay, so we have our function g of x, which is x e to the power of x. I think I called it f of x earlier, but let's use a different letter now. G of x equal to x e to the power of x. And we've seen that the inverse then we're calling w. In other words, g inverse x we're calling w of x, which is just w of x e to the power of x. And that will give us our x. In other words, if you stick our original function into the Lambert W function, you'll get the original input, which was x. Also, we know that g of w of x, it's kind of the same thing again, is going to be equal to w of x e to the power of w of x, which again is just x. Or we can say here that e to the power of wx is equal to x over w of x. These are just a couple of properties that might be useful. So particularly this one here, I'm going to do a couple of examples where we use this property here, where we have a function that looks like this, and we can use the Lambert W function to solve it, to work out what x is. So let's just look at a different function. Let's look at f of x. We'll call it f of x is equal to e to the power of x, or we can say that y is equal to e to the power of x. What I'm going to do is find the inverse of this here, and the reason I'm going to do that is I'm going to use that in one of the examples I'm going to do where we use the Lambert W function. So let's look at our function. We have this function y is equal to e to the power of x, and I've done a video on how to find inverses. Basically what you do is you have to isolate the x, and then you replace the x with y and the y with x. So you can have a look at that video if you're still unsure about how to do that. But what I'm going to do here is just get the log of both sides here. So I'm going to get the natural log of y is equal to the natural log of e to the power of x. Now that would just give me log of y is equal to, well, this here is just x, because you've got an e down here, this is a base e. What would I raise this e to the power of to give me e to the power of x? Well, it's just going to be x. So that means then that our inverse function of x is just going to be, remember, replace the y with x and the x with y. So this is our y here. We're just going to look at log of x being on the right hand side here. So this means that if we take the original function and put in our inverse function, we'll just get our function, which is e to the power of x. We've got to put in our inverse function, which is log x, and that should give us x. If we put the inverse function into our original function, we just get our original input, which is x. So this identity here, this equation here, is what I'm going to use in an example where I use the Lambert W function to solve an equation. So let's have a look at an example. Let's say we have 2 to the power of x plus x equal to 5. So let's work through this. Let's take the 2 to the power of x on this side, take 5 minus x here, then divide both sides by 2 to the power of x will give me 1 is equal to 5 minus x over 2 to the power of x. Or just 1 is equal to 5 minus x times 2 to the power of x, 2 to the power minus x actually. So let's see what we can do with this. Now we have a 5 minus x down here. I'd like a 5 minus x up here. So what I'm going to do is multiply both sides by 2 to the power of 5. So that will give me 5 minus x times 2 to the power of minus x times 2 to the power of 5. We can just add those two powers, so that will give me 2 to the power of 5. So equal to 5 minus x times 2. We just going to add these two powers here to give me 5 minus x. So now I have a 5 minus x here and a 5 minus x up here. This I've got to really change to e, so I've got to do a little bit more work to do that. So let's work on that. So what I need to do really here is change this to an e. So I'm going to use what I did earlier. Remember earlier we had e to the power of log x equal to x. So what I can say here is e to the power of log 2 is equal to 2. So I'm going to change this to e to the power of log 2. We've got 2 to the power of 5 is equal to 5 minus x e to the power of log 2 all to the power of 5 minus x. So now I've got 2 to the power of 5 equals 5 minus x e to the power, multiply these two, you get log 2 times 5 minus x. So all I really need to do now is put a log 2 down here, and then I will have a log 2 5 minus x up here as well, and I'll have my e here. So I'm going to multiply both sides by log 2. Now 2 to the power of 5 is just 32, so on the left hand side I'll have, let's see, 32 log 2 is equal to log 2 5 minus x e to the power of log 2 times 5 minus x. So now you can see I have log 2 5 minus x here, I've got log 2 5 minus x here, and I have an e here. So this is now in the form x e to the power of x. So I can apply the Lambert W function to both sides. So let's do that. So I get w of 32 log 2 is equal to w of log 2 5 minus x e to the power of log 2 5 minus x. So if we apply the Lambert W function to the right hand side, we're just going to get this here. Remember, if you apply the Lambert W function to x e to the power of x, we'll just get x. So if we apply it to this, because we have the same thing here and here, we're just going to get log 2 5 minus x. Okay, so let's do that. So on the right hand side we just end up with 5 minus x log 2. So now all we've got to do is just isolate x. So first thing I'd do is take Lambert W of 32 log 2, divide by log 2, that'll give me 5 minus x, and then Finally, if I just isolate the x here and change signs, I will finally end up with 5 minus w of 32 log 2 over log 2. And that's my answer. You can do this on a calculator that has a Lambert W function button. So let's have a look at another example. So let's have a look at this one. X2 here is equal to 5. This just means we're doing x to the power of x equals 5. So what we can do here is just get the log of both sides. So let's get the natural log of x to the power of x equals log 5. Bring the x down, you get x log x equals log 5. Now another way of writing x here is just e to the power of log x. We had that earlier. So I can write e to the power of log, well, I'll actually just switch these around. I'll put the log x first, and then I'm just going to take this one and change that to e to the power of log x. So it's this times e to the power of log x. That's equal to log 5. So you can see here we've got a log x here, we've got a log x here, we have an e here. So now we can just apply the Lambert W function to both sides. So it's log x e to the power of log x is equal to the Lambert function of log 5. So if we do that to the left hand side, we just get log x. To the right hand side, still w of log 5. Okay, so finally all we've got to do is convert this into index form. We have the log of x to the base e is equal to w of log 5. So we were just going to take e to the power of w of log 5 is equal to x. So again, this is something you can just do on a calculator that supports the Lambert W function. Okay, so that's it for this video.